Doping of chromium in graphene using electron beam manipulation for functional defect engineering. This paper was published in Applied Nano Materials in 2018. The ultimate precision for fabrication technology is the precise arrangement of single atoms in relation to one another. The ability to specify where all the atoms should sit would give one control over the emergent material properties and the ability to create functional structures designed from first principles. In particular, fields such as spintronics, quantum computing, and quantum sensing depend critically on the precise arrangement of atoms for the desired properties to emerge. But how do we manipulate single atoms? Previous work explored a strategy for inserting foreign dopant atoms into graphene with near-atomic precision using a focused electron beam in a scanning transmission electron microscope. Initial demonstrations were performed with silicon atoms that happened to be in the contamination on the graphene surface. This was extended from silicon atoms to platinum atoms, which were intentionally deposited on the graphene surface using focused electron beam-induced deposition. Here, we extend the technique to chromium atoms and examine how these atoms interact with the surrounding material and the electron beam. We begin by transferring graphene onto a perforated TEM grid so that some areas are freestanding. Then, we used an E-beam evaporator to evaporate a thin layer of chromium across the graphene surface, not enough to form a continuous layer, but enough to create many discrete nanoparticles. We then examined the sample in the scanning transmission electron microscope. We used the same beam dragging technique from previous investigations. The beam is positioned on the parent nanoparticle and then dragged out onto the pristine graphene. Carbon atoms from the lattice are ejected, creating vacancies. The beam is then moved back to the parent nanoparticle and used to sputter atoms off the nanoparticle and onto the graphene surface, where there is some probability they will diffuse to the vacancy site and become chemically bonded to the graphene lattice. Here is the initial configuration. The beam is initially placed here on the bright nanoparticle, and then dragged out onto the graphene and back in an iterative process. Every few seconds, we acquired a new image to see what changes we have made to the sample. In this way, we were able to attach several chromium atoms to the graphene. Eventually, we damaged the lattice too much and generated a hole. Chromium and silicon atoms spontaneously attached to the edge of the hole, and the impacts of the electron beam could rearrange them. Now that we know that we can attach chromium atoms to the graphene lattice, we would like to start exploring what different structures might be possible to form. There are many possible stable structures for dopant atoms attached to the graphene lattice. So many, in fact, that an exhaustive theoretical exploration is not tractable. Moreover, even if we knew every stable structure, it would not be obvious which ones we would be able to drive the system into. Instead, we can take the opposite approach and document which structures we observe and perform theoretical investigations into this much smaller subset of structures to see if they might be of interest. By simply scanning the beam over a created chromium dopant, we can watch the system evolve and begin to document the different structural transformations. Based on these observations, we can turn to theoretical simulations to further inquire about what emergent properties might be of interest. For chromium in a single vacancy site, we found a significant spin polarization imbalance, which suggests that it would be possible to electronically control the spin state. For chromium at a trivacancy site, a significant band gap appeared. In a similar way, we can also examine some of the different heteroatomic structures that can be formed involving both chromium and silicon atoms. These investigations take the first steps toward documenting and understanding the dynamic evolution of few atom systems embedded in graphene using an electron beam. Top-down control of the transformation process remains an active area of research. Machine learning approaches to automated data acquisition and real-time analysis may offer a pathway forward. Links to the publication may be found in the comment section below.